Have you ever wondered why we have towering mountain ranges, deep ocean trenches, and frequent earthquakes? It all comes down to the heat inside our planet. Earth isn't a cold, static ball of rock. It's a dynamic system powered by immense heat deep within its core. This internal heat sets everything in motion, acting like an engine that constantly reshapes the surface. We're going to explore this engine, focusing on how this deep heat leads directly to the theory of plate tectonics. To understand the engine, we have to look inside. Scientists have divided the Earth into four main layers: the crust, the mantle, the outer core, and the inner core. Think of the Earth like an onion, but each layer is fundamentally different. The thin, cool crust is where we live. Beneath that is the massive mantle, and at the very center is the super hot core. The composition and temperature of these layers create a system where heat flows from the inside out, driving all the geological activity we see. Let's start with the crust. It's the thinnest layer, kind of like the skin on an apple, but it's crucial. Our crust isn't one continuous shell. It's fractured into huge, interlocking pieces, the tectonic plates. We distinguish between oceanic crust, which is thinner and denser because it's rich in iron, and continental crust, which is thicker, less dense, and makes up our land masses. This density difference is incredibly important when these plates run into each other. Directly below the crust is the mantle, the thickest layer of Earth. It's about 2,900 kilometers deep. Here's the surprise. The mantle is mostly solid rock, not molten liquid. However, due to the extreme heat and pressure, this solid rock is plastic, meaning it can flow incredibly slowly over millions of years, like a super thick, stiff tar. This flowing rock is what makes the whole system dynamic, and it's where all the action begins. The ultimate source of the power is the core. The core is mostly made of iron and nickel, and it's split into two parts. The outer core is liquid metal, and its movement generates Earth's magnetic field. The inner core is solid, despite being hotter than the surface of the sun, because it's under such unbelievable pressure. The core's heat, whether left over from formation or newly generated, is the energy needed to drive the planet's internal processes. Where does all that heat come from? While some is left over from when Earth first formed, a major source is continuous, quiet energy from radioactive decay. Deep inside the planet, certain unstable elements, like uranium and thorium, slowly break down. This natural, ongoing process releases enormous amounts of thermal energy. Think of the Earth as having a slow-burning nuclear reactor at its center. That heat keeps the mantle churning. So we have a heat source and a thick plastic layer. How does the heat move? Through a process called convection. Convection happens in any fluid, whether it's water, air, or the plastic rock of the mantle. When material heats up, it expands, becomes less dense, and naturally rises. As it moves away from the heat source, it cools, becomes denser, and sinks back down. This continuous loop, rising hot, sinking cold, is the definition of a convection current. Now, imagine that convection process happening on a massive scale within the mantle. Hot rock from the deeper mantle rises toward the cooler crust, transfers some of its heat, and then slowly sinks back toward the core. These mantle convection currents are very slow, moving only a few centimeters a year, about the rate your fingernails grow. But over millions of years, these sluggish, powerful currents generate enough drag to pull, push, and slide the massive tectonic plates that sit above them. That is the engine of plate tectonics. This brings us to the unifying theory of plate tectonics. The theory states that the Earth's rigid outer layer, called the lithosphere, is broken into numerous large slabs or plates that are constantly moving relative to one another. You are standing on one right now. This entire global system is driven by the transfer of heat and the movement of the mantle beneath. meaning the surface of our planet is always changing, just very slowly. Let's clarify the two layers involved in the motion. The lithosphere is the rigid layer. It includes the crust and the very top, solid part of the mantle. This is the plate itself, the part that moves and breaks. It rests on the asthenosphere, which is the upper part of the mantle that is hot and plastic, the layer where the convection currents are strongest. You can think of the lithosphere as a giant, brittle ice sheet floating on the much hotter, soft, and flowing water of the asthenosphere. The most dramatic geological action happens where these plates meet, at the plate boundaries. It's where plates interact that they create mountains, cause earthquakes, and form volcanoes. Scientists classify plate boundaries into three major types based on how the plates are moving relative to each other. They can move apart, crash together, or slide past one another. Each interaction builds unique features on Earth's surface. First up are divergent boundaries, where two plates pull away or diverge from each other. When this happens, magma from the mantle rises to fill the gap, cools, and forms brand new crust. This process is happening right now in the middle of the Atlantic Ocean, creating the Mid-Atlantic Ridge, a huge undersea mountain range. When this happens on land, it creates a rift valley, slowly tearing a continent apart. Next are convergent boundaries where plates collide. These are responsible for the most extreme geological features. The outcome of the collision depends entirely on what type of crust is involved: ocean against continent, ocean against ocean, or continent against continent. Think of a head-on collision between cars. The amount of damage depends on the size and speed of the vehicles. And here, the damage creates mountains and trenches. The most common type of collision is ocean-continent convergence. Since oceanic crust is denser than continental crust, when they meet, the oceanic plate always sinks underneath the continental plate, a process called subduction. This creates a deep-sea trench at the boundary and causes the rock above to melt, leading to the formation of a chain of volcanoes on the edge of the continent, like the Andes Mountains in South America. When two continental plates collide, things get messy. Since both plates are relatively low density, neither is easily subducted. Instead, they just buckle, fold, and are forced upward, creating immense, non-volcanic mountain ranges. This is how the Himalayan mountains were formed, as the Indian plate crashed into the Eurasian plate. It's a slow, powerful push that lifts the highest peaks on Earth. Finally, we have transform boundaries, where plates slide horizontally past one another. Crust is neither made nor destroyed here, but the friction between the two massive grinding plates is enormous. The plates lock up, pressure builds, and when they finally slip, that sudden release of energy is what we feel as an earthquake. The famous San Andreas Fault in California is a perfect example of a transform boundary. How do we know all this is true? The evidence is overwhelming. One of the earliest clues was the way the continents look like they could fit together like a giant puzzle. Furthermore, scientists found identical plant and animal fossils on continents now separated by thousands of miles of ocean. The only way this makes sense is if those landmasses were once joined in a supercontinent called Pangaea before the plates drifted apart. The Earth's internal processes don't just create mountains. They drive the entire rock cycle. When magma rises at divergent boundaries and cools, it creates igneous rock. When plates collide, the heat and intense pressure transform existing rocks into metamorphic rock. And as mountains are uplifted, weathering and erosion break them down to form sedimentary rock. Plate tectonics is the engine that constantly recycles Earth's materials. Understanding plate tectonics is essential for living safely on Earth. The movement of the plates creates geological hazards. Earthquakes are concentrated along all boundary types, especially transform faults. Volcanoes occur mostly over subduction zones or where magma rises at divergent zones. By knowing where the plate boundaries are, scientists can better monitor seismic activity and warn people about the potential for future earthquakes and eruptions. Let's wrap up our main takeaway for MS-ESS2-2. The heat from Earth's core drives mantle convection. These convection currents act like huge conveyor belts, slowly dragging the lithospheric plates across the planet's surface. And it is the three distinct ways these plates interact at their boundaries, divergent, convergent, and transform, that form every major surface feature we see. For your challenge, think about a U.S. feature like the Rocky Mountains, the Cascade Volcanoes, or the San Andreas Fault and determine which plate boundary created it.